All right, so this video is about the generalized Fourier series. So the topic of interest would be function approximation inside of the function space L2. All right, so we talk about an orthonormal set. We start with an orthonormal set, pi. So this is, again, an orthonormal set of functions in a Hilbert space S is a complete basis or a total basis. This is different than the Hamel basis that we had before. If for every x in S, we can write x in terms of this series approximate, or this series in our functions, our basis vectors, pi. And the coefficients here would be the inner product of x with pi. So notice that, if you were to let x equal to ci pi, and we know that it's an orthonormal basis, so inner product of pi with pj is equal to delta ij, which is equal to 1 if I is equal to j, 0 otherwise. Then when I take the inner product of x with pj, I plug in x is equal to, c pi here, and so the pi's pull out, and I get the inner product pi with pj, which is going to be, of course, 1 only at j, and so we get our coefficient cj. So in other words, if we're using a basis vector here, these cj's are equal to the inner product of x with pj, or the projection of x onto that particular basis function. So we can write the generalized Fourier series, in this form. Now, this is the most common is the standard Fourier basis. So, for example, this would be Fourier series. You can do something with Fourier Transform where we take an integral here, but this is for the standard Fourier series. What do we use? We use for example, ECEn 380. We use these particular functions, right? 1 over the square root of t, e to the j, 2 pi over t and t. This would be the nth basis function. Now, any function f in L2 can be written as a Fourier series. It can be, this should be a square root here. Cn times each of those pn's, and the coefficients are going to be given by taking that function and projecting it back onto each of those basis vectors, and so we get that Cn is equal to this guy. So these two equations here are the standard Fourier transform pair. Now, the way they're written in 380 is notice there's a square root of 1 over square root of t here, and there's a 1 over square root of t here. Normally, you put the 1 over square root of t's together, and so you let f of t be some linear combination of our basis vectors, which are complex exponentials, and then the functions here. Oh, I see. There shouldn't be a square root like that. I'm sorry. It will be just 1 over t. All right. Well, anyways, this is only one example of a Fourier series, or a complete Fourier series. So, in general, we can talk about generalized Fourier series, where any orthonormal set basis vectors, orthonormal basis vectors, we can write, x is equal to the inner product of x with pj times pj. Or another way to think about it is x is equal to the summation j equals 1 to infinity cj pj, and then cj is going to be the inner product of x with pj. And this gives you, in one case we have a function of time, since PJs are functions of time, and then we've got our Fourier coefficients. So these would be Fourier transform pairs. All right, so given a generalized Fourier transform, there's a couple of important relationships between the function and its Fourier transform. So again, we have an orthonormal set of vectors, and we say, I guess, did I talk about vectors being complete? Oh yeah, it's a complete vector if every x in S can be written like this. So now we have a set of of vectors that are not necessarily complete. In other words, there might be some x's that that are outside of the linear combination of all those p's. Okay, now if we look at the Fourier transform, in other words, we take x and inner product with each of these pi's, and we look at this sequence, C1, C2 for infinity. So in other words, x of t is an element of L2, but this this set of coefficients, you see, c is going to be an element of little L2. Okay, it turns out that the L2 norm of little c's is always going to be less than or equal to the big L2 norm of x of t. So this is known as Bessel's inequality. And to prove this inequality, we first look at, so you take x and we subtract from x essentially the approximation of x, okay, the sum of CJs with PJs. And let's look at so x is is a function of t, PJs will be a function of t, so this whole thing is a function. And so let's look at the L2 norm of that function squared. So that's going to be the inner product of x with the sum, x minus the sum with itself. And now we take, this will be inner product of x with x, and then we would have the inner product of x with all of the sums CJ, PJ, and we'll pull the CJs out. That gives us a complex conjugate. And then this term, we'll pull the CJs out, and we have x times PJ, but we've reversed the order, so this is all complex conjugate here. And then when we combine these two terms together, we can pull the CJs from the first term and then the CK complex conjugate out, and we'll have PJ with PK, and this is all in the L2 inner product. So that's equal to, this guy is the norm of x2, and then on this vector, we have x with pj. This guy is just cj. And here, x with pj is again cj bar. And so we have these two sums like that. And then pj with pk in the L2 norm. This thing, it's only, this is going to be delta ij because they are linearly independent, and so it's going to be when ck, in other words, this is j equals 1 to infinity, this would be k equals 1 to infinity, and all of the terms where k does not equal j go away. So all we're left with is a j equals 1 to infinity cj bar. All right, so this guy is equal to the norm of the L2 norm of x, and then notice we've got we subtract, and add, and so these two will cancel out, and now we're just going to subtract cj bar, and cj's any cj bar. This is going to be the norm of cj, or the absolute value of cj squared for complex conjugate or complex numbers. So we get the L2 norm, and then we have the sum of the CJ squareds. And then we notice that this guy, that's just the little L2 norm of C. So this, we have then that the norm of x minus CJ PJ is going to be the norm of x the L2 norm of x minus the little L2 norm of c. And since this norm here has to be greater than or equal to 0, because it's a norm, this guy is greater than or equal to 0, which implies that the big L2 norm of x is bigger than the little 2 norm of c. So we've shown that this is always the case. All right, so now let's talk about what's called the Parcels Equality. So if these vectors are complete, meaning every x can be represented as a linear combination of p1 up to p2, p infinity. So this inequality here is holds even when the basis is not complete, because the inequality is essentially because there's some x's maybe that aren't represented in the linear combination. So if it's complete, then every x can be written as a linear combination of the basis vectors. In that case, we get that the capital L2 norm of the function is equal to the little L2 norm of the sequence of Fourier coefficients. Okay, so this is a very famous theorem, and this is I guess used quite a bit in Fourier theory. All right, so if t is complete, then the norm has to equal to 0, and so back here, instead of less than or equal to 0, this thing was equal to 0, and so you would get an equality instead of an inequality, and that's the proof of Parcels inequality. So what is the significance? Well, when we say that the big L2 norm of x, the function, in other words, the norm of the function is equal to the norm of the Fourier coefficients, what we're basically saying, the 2 norm is in essence a representation of the energy of a signal. So we're saying the energy in x is going to be equal to the energy in the Fourier coefficients. In other words, by doing the Fourier transform, we don't lose anything in terms of energy. All right, so if we write the relationship between x of t and its transform, c, again, this is a sequence, this is a function, then we can write the following theorem. So if x is the x has Fourier transform pair with c and y with b for the same complete basis, then when I take the inner product of x and y in big L2 space, okay, this is an integral, that's the same thing as taking the inner product of the coefficients in little L2 space. Okay, so the proof, x is going to be the sum of ci pi, y is going to be the sum bi pi, and so when we take the inner product in big L2, when we plug those in, we can pull the coefficients for x out as c, and pull the coefficients for y out. They'll come out as bj complex conjugate, and then we have all the inner products of pi with pj. But of course, the inner product of pi pj, this thing is delta ij. So it's the only time it's 1 is if pi is equal to pj, and in that case, we have this double sum collapses to a single sum, and so we have ci and bi complex conjugate, and of course, when pi is equal to pj, the inner product is just 1. And then we notice, what is this sum? Ci and bi complex conjugate. That's just the little L2 norm. So there is the proof that inner products of functions can be written as the inner product of Fourier of the Fourier coefficients.